All right, before we get started, does everybody have the AMI? Passed out yesterday and the day before. So, question on the homework before we get started. Questions on any of the homework assignments? What we're talking about today is simplifying these rational exponents, these rational powers. Now, everything we have up here, and I have it written up on the whiteboard, y'all have done before. Y'all have worked with these before. They're properties of powers. As our first one that we have listed is product of powers. If we multiply like bases, we add the exponents. That's all product of a power is. Power of a power. When we have a term to a power, our powers of powers multiply. Power of a product. If we have two things being multiplied together and they are both being put to the same power, we can apply that power, that exponent, to both terms. Negative exponent. If the exponent's negative, we can move it from the top of the fraction to the bottom or bottom to the top. And that exponent changes from positive to negative or negative to positive. And again, we've used these. We've been using these properties already. Zero exponent property. A to the 0 equals 1 as long as A is not 0. 0 to the 0 does not work. Quotient of powers. A to the m divided by A to the n. When we divide like bases, we subtract the exponents. And power of a quotient. When we're dividing two things and they're both to the same power, we can apply that power to both terms. So most of these properties of exponents we've had, y'all have used them, we've used them before. And what we're going to do is we're going to use these properties to simplify these rational expressions. Now, this is mainly pertaining to radicals, our square roots, cube roots, but we can talk about powers too. So no radicands have perfect nth powers. Factors other than 1, really all that's saying is that we can't leave it as, say, the square root of 16. Or the cubed root of 16, because the square root of 16 is 4. Cubed root of 16 actually will simplify to 2 cubed roots of 2. Because if we can reduce it, if there are perfect nth roots, perfect nth powers, we need to simplify it down. No radicands, no radicals can contain a fraction. We can't leave it as the 4th root of 2/7. We cannot have a fraction in a radical. That's all it's saying. And no radicals can appear in the denominator of a fraction. We can't leave it as like 1 over 7 plus the square root of 3. We cannot have a radical in the bottom of a fraction. Okay. So we're going to use these properties of rational expressions to simplify these as far as possible. So the first one we have is 7 to the 1/4 times 7 to the 1/2. when we multiply like bases, we add the exponents. And we're used to doing this with like x times x squared. X times x squared is x to the third. We're used to doing it with those with whole number exponents. Well, it works the same with this here. It doesn't matter that the exponents are fractional. We multiply like bases, we add the exponents. So at this point here, we just need to add 1/4 and 1/2. Well, luckily for us, the calculator will do 1/4 plus 1/2, which is 3/4. Telling us that 7 to the 1/4 times 7 to the 1/2 is 7 to the 3/4. Now this is simplified as it gets, mainly because 7 is a prime number. We can't reduce it, we can't rewrite it, it's just 7. 3/4, that's not a whole number, so that doesn't reduce at all. And the 4th, the 4 on bottom is telling us it's our radical, it's our roots. We're trying to find what times itself 4 times is 7. There's not a number. The 3 on top doesn't help. So, that's it. 7 to the 3/4. And unfortunately for this here, because we can't type 7 to the 1/4 times 7 to the 1/2 in the calculator, it's just going to give us an irrational number. Because 7 to the 3/4 is also irrational. Questions on A? B, 6 to the 1/2 times 4 to the 1/3, all to the second power. 6 and 4, not like bases. So we can't add our exponents. No same powers, but if we look at all of our properties, we do have power of a product that says if we have two things multiplied together to a power, we can apply that power to both terms. So really we have 6 to the 1/2 to the second being multiplied with our 4 to the 1/3 to the second. We can apply that power to both terms. Now, individually, we still have a power to a power. So for our 6, it'd be 6 to the 1/2 times 2. And with our 4, we have 4 to the 1/3 times 2. Well, what is 1/2 times 2? 1. So we can just say it's 6 to the first or 6. Our 1/3 times 2 is 2/3. Questions on B? Now we can make sure that this is simplified because 6 to the first, that's as simplified as it gets. 4 to the 2/3, is there a number times itself 3 times that gives us 4? Well, no, 2, because 2 times 2 is 4, yes? So you don't have to write this part, because I mean we could say that this is 4 is 2 squared. Powers of powers do multiply again. But 4/3 still does not reduce. It doesn't get simpler. It's not simplified. And is really 4 to the 2/3 any simpler than 2 to, is 4 to the 2/3 any simpler than 2 to the 4/3? No. Nothing reduced, nothing simplified, so our answer is just this here. The only reason we would have to take it to this point if something of that fraction reduced. So instead of having, say, 2/3, if it was, say, 2/4 or 2/8, 2/6, that 2 squared, that 2 and that exponent would reduce that fraction. we would. Here, it doesn't. So we can stay right there. So questions on B before we get to C. C. We can treat C the exact same way we did B. 4 to the fifth times 3 to the fifth all to the negative 1/5. So we can apply that negative 1/5 to both of our terms, because we're going to apply it to our 4 to the fifth and apply it to our 3 to the fifth, telling us that we have 4 to the fifth to the negative 1/5 and 3 to the fifth to the negative 1/5. Powers of powers do what? Multiply. Five times negative 1/5 is what? Negative 1. Because 5 times 1/5 is 1, because we'd have 5 over 5, which reduces to 1. So 5 times negative 1/5 would be negative 1. Questions on how we got to 4 to the negative 1 times 3 to the negative 1. Can't leave an exponent negative. So to make it positive, we would do what? Move it from the top of the fraction to the bottom. So the 4 would go on bottom, and so would the 3. So what we have left is 1 over 4 times 3. Well, what is 4 times 3? 1/12. That also means, well, 1/12 is a nice number, yes? Relatively speaking, especially considering 4 to the 2/3. I could have typed 4 to the fifth times 3 to the fifth all to the negative 1/5 on the calculator, and it would have given us 1/12. Not all of these will simplify nicely in the calculator. Some will. Questions on any of those so far before we look at these two? D, 5 over 5 to the 1/3. We're dividing two numbers, yes? Are the bases the same? Because the base on top is what? 5. The base on bottom is? Now they didn't say it or didn't write it. What's the exponent on top? 1. So we can actually say that this is 5 to the 1 minus 1/3, because when we divide like bases, we can subtract the exponents. When we divide like bases, we can subtract the exponents. So 5 to the 1 minus 1/3, well, what is 1 minus 1/3? 2/3. Five to the 2/3 is an irrational number, because we're trying to find out what times itself 3 times is 5, and then take whatever that number is and square. Or we could square 25, what times itself 3 times is 25, still a rational number. So we get this here, yes? And what we started with was 5 over 5 to the 1/3, yes? Get this here. Well, our answer was 5 to the 2/3. Are those decimal approximations the same? Yeah. And the reason I'm showing you this, I really should have shown this to the other 2 hours. Even though it didn't give us the answer, it did verify it. We can say for certain now that 5 over 5 to the 1/3 is the exact same value as 5 to the 2/3. They give us the same decimal approximation. It gives us a way to check it. Make sure we did get the correct value. 5 is prime, so that is as far as it goes. We can't do anything with it. E. One of the main issues with E is we cannot have a fractional exponent in the bottom of a fraction. We need a way to get rid of that. 42 and 6 are not like terms. They're not like bases, are they? 42 and 6, are they divisible? Yeah, we can divide 42 and 6. That'd be nice, but we have the 1/3, yes? A divided by B to the m is A to the m over B to the m. Power of a quotient property. We're used to saying A over B to the m and applying the power to both. We can go the other direction. Since they're both put to the same exponent, we can pull it back up into a single one being applied to 42 over 6. Now, the whole reason I'm doing this is because pulling that power out leaves us with what inside? 42 over 6, yes? What is 42 divided by 6? So that took it from 42 to the 1/3 divided by 6 to the 1/3. Whatever number times itself 3 times is 42, being divided by a number times itself 3 times to get a 6. Well, 42 divided by 6 is 7. It gave us a way to be able to divide that nicely. Questions on how we got to our 7 to the 1/3 to the second power? So again, this whole section is just taking these properties of powers and trying to simplify them as best we can. Powers of powers do what? Multiply, yes? So it's 2 times 1/3. It is 2/3. And that's it. Really, it's multiplied also by 1, but 1 times 2/3 is still 2/3. 7's prime, so we can't do anything with this. Questions on this here? We look at some more of these here. 2 to the 3/4 times 2 to the 1/2. We're multiplying like bases, so we would what? Add the exponents. When we multiply like bases, we have the exponent. So we're adding 3/4 and 1/2. Really, if we're doing this here, we'd set the bases equal to each other, set both of them to the base, not the bases, but we would set the denominators of our fractions in the exponent to both have a denominator of 4, and then add those two together to give us 2 to the 5/4. Questions on number 1? Number 2, 3 over 3 to the 1/4. 3 divided by 3 to the 1/4. When we divide like bases, we subtract our exponents. Now, all the ones, this one and the last one we had, the numerator's exponent was 1. It doesn't have to be. We can have it be whatever we want. We just know that when we divide like bases, we subtract the exponents. Numerator's exponent goes first, denominator's exponent goes second. And 1 minus 1/4 is 3/4. So we have 3 to the 3/4. We ready for problem number 3? I do find problem number 3 a little interesting. Now, since the bases aren't the same, 20 and 5 are not the same, but they are put to the same exponent, we can pull that 1/2 back up to an exponent for the whole fraction. And part of the other reason we're doing that is 20 is divisible by 5. And 20 divided by 5 is 4. So we have 4 to the 1/2 to the 3rd, yes? So the 1/2 power is just telling us that if we were to apply that or to simplify it, we need to find a number times itself that gives us 4, yes? Unfortunately, there's not a number that multiplied by itself that gives us 4, right? Oh, wait, there is one, isn't it? Because 2 times 2 is 4. So there's 2 ways we can go from this here. One is that we can say 4 to the 1/2 is 2. We just take the leap and say, well, I know that 4 to the 1/2 is saying that I'm taking the square root of 4, which is 2. And we can say that we have 2 cubed, which is 8. Thank you. So, the other way we can do this, as well as we just said, 4 is indeed 2 squared. Well, 2 squared to the 1/2 to the 3rd. Well, 2, that power, 2 to the 2nd time to the 1/2. Our powers of powers multiply. So 2 times 1/2 is 2/2, or 1, which tells us, gives us 2 to the 3rd, which is 8. So do we see the difference between those two? The bottom one's just saying, well, I know that 2 to the 1, or 4 to the 1/2 will give us 2. That simplifies, and we're done. And that's it. Cut this out. So, let's look at this one here. Number 4, 5 to the 1/3 times 7 to the 1/3. Not 1/3. If it was 1/3, that'd make it even nicer. 7 to the 1/4, all to the 3rd. Power of a product. So we have a product here that is to a power. So we can say that this is the same. Well, nice if I give myself a little more room. 5 to the 1/3 to the 3rd. 7 to the 1/4 to the 3rd. Well, with our 5, we'd have 1/3 times 3, and 1/3 times 3 is 1. So it's just 5, or 5 to the 1st, or just 5. Our 7 to the 1/4 to the 3rd. Well, our 1/4 times 3 is 3/4. 7 to the 3/4 doesn't reduce, it doesn't simplify. 7's prime, so there's no way to take a 4th root of it. That's actually it. Uh, 7 to the 1/4 to the third, powers of powers, multiply. So we're going to multiply our 1/4 and 3. Mm-hmm. Powers of powers, multiply. So really the in-between step that we could put, try this again, is that we could say that this is the same as 5 to the 1/3 times 3 times 7 to the 1/4 times 3. And our 1/3 times 3 would give us 3/3, which is 1. We don't have to write it. Our 1/4 times 3 is 3/4. Mm-hmm. And then we would simplify if needed. Because 7 is a prime number, we can't rewrite it as a number to a power. Nothing we can do there. But on the previous one, here we had 4 to the 1/2. We're trying to see what number times itself is 4. That is 2. We can simplify it, it works out. Now, I will say that not every perfect square, because 4 is a perfect square, would be helpful. So I'm going to change it just in this one part. So if we said that this was, say, 5. We're looking for a number times itself 5 times to give us 4. Well, there is no number. There's no nice number. So we could switch it to 2, because 5. But this would give us 2 to the 2/5 to the third, which is 2 to the 6/5. It doesn't help us. Because if we just left it as 4, it'd be 4 to the 3/5. 4 to the 3/5 is not any nicer than 2 to the 6/5. No reason to do that. All right. Questions on this here? So I know a few of us joined us from the trip. The homework is 3 through 10. But, yes, 3 through 10. Now, I'm going to keep going through these problems here, because I think the ones, especially that we've gone through so far, if you want to go straight to the homework and do that. For those who joined us, I'm going to do a few more. Yes. Yeah. Because the whole thing with this section of this chapter is we're trying to simplify these powers. We're trying to simplify it as best we can. And what we're using are these power properties. So product of a power, if we multiply like bases, we have the exponents. So since both the bases are 3, we'd add the exponents. Telling us that we have 3 to the 1/2 plus 3/2. So we're really adding the 1/2 and 3/2. Now we're used to doing this product of a power with x's, because x to the 4 times x to the third would be x to the 7, because we can add those exponents. We're used to doing that. But it doesn't matter if they're rational or, well, if they're integers or rational, we can still add these together, giving us 4/2. Well, 4/2 would reduce to 2. 3 squared is 9. Yeah, it just reduced, yeah. Now, if it doesn't reduce, we have to just leave it. So 7 to the 2/3 times 7 to the 1/2. 7 to the 2/3 plus 1/2. Now, at this point here, we would have to add the 2/3 and 1/2. Two ways we can do it. One is our properties of fraction, our rational addition, our fraction addition. We have to get the bases to be the same and add them. or we can say 2/3 plus 1/2 is 7/6. So we have 7 to the 7/6. Top of the fraction is our powers. So rewriting fractions as rational expressions as radicals, because we've had this the other day if we're switching back and forth. The reason I'm writing this is the n on bottom, the number on bottom, is our index, our root. It's telling us how many times, or what times itself gives us that number. Like 2 would be a square root. 3 is a cubed root. Here we have the denominator of 6. So really we're trying to find a number times itself 6 times. Well, and then the number on top is what power we're putting it to. Well, there is a whole number that comes out, but it does not reduce nicely. We'll leave it as this here. Because the only other way to rewrite it would have been 7 times 7 to the 1/6. But I don't feel like that's any simpler than just leaving it as 7 to the 7/6. So we'll just leave it there. 10 to the 1/2 over 10 to the 1/4. 10 to the 1/2 minus 1/4. Now we can't plug these into the calculator because, well, I mean we can, they're just not a number times itself 4 times that gives us 10. That is an integer or a rational number. It's irrational. Now I did show this earlier, because what we started out this problem with is 10 to the 1/2 over 10 to the 1/4. And we get this number here. Now we said our final answer for this here was 10 to the 1/4, yes? Are those decimal approximations the same? Now even though 1.7782791 is not the answer we're looking for, it's 10 to the 1/4.
Would we be able to do this on those calculators and then transform it back to?
And unfortunately, because, yeah, we have it won't do it. It does it with radicals, it won't so much do it with this here. But what this does tell us is that the decimal approximations are the same. So that means 10 to the 1/4 is the same, is the equivalent of value of what we started with. So it is the correct answer, it is the simplified version. It gives us a way to check it. Even though it won't give us the exact value, it does give us a way to check and verify that it is the right value. Questions on this here? Four to the 3/2 squared. Powers of powers do what? Multiply. So we could say this is the same as 4 to the 3/2 times 2. Well, what is 3/2 times 2? And 4 to the 3rd is 64. I feel like by the end of this chapter, we're going to be very comfortable with the fact that 4 to the 3rd is 64, and the cubed root of 64 is 4. It's come up so many times. But do we feel comfortable with this here? Yeah. I mean, these properties that we have, we can't leave an exponent negative. It's just we're utilizing this here to simplify. Yeah. So that's it.